In this video, we are going to talk mainly about Myszkowski transposition cipher. To begin with, what is transposition cipher? Transposition cipher is a method of encryption by which the position held by units of plaintext are shifted according to the regular system, so that the ciphertext constitutes a permutation of plaintext. In simple terms, the plaintext is being reordered. Transposition ciphers are a bit different to substitution ciphers. Substitution ciphers replaces each letter with different letter or symbol to produce ciphertext. In a transposition cipher, the letters are just moved around. Here is an example of simple transposition cipher. If you notice, the letters in the plaintext is the same letters used in the ciphertext. They were just rearranged. Now let's go to the types or kinds of transposition cipher. The first one is real fence cipher. Real fence ciphers have the plain text letters rearranged in a zigzag pattern down to two rails or two rows, and then the ciphertext is read off in rows. The second one is a root cipher. In this cipher, the plain text is written into a grid of a predetermined shape and then read off following a certain route. The third one is the columnar transposition cipher, which involves writing the plaintext in rows under the keyword and then reading of the columns in the order determined by the keyword. The fourth one is the main topic of this video, which is Myszkowski transposition cipher. This is a variant of columnar transposition cipher where the plaintext is written out in rows under a keyword. And the fifth one is the permutation cipher. This is another form of transposition cipher, which involves rearranging the character in the plaintext according to the specific predetermined order. This order, also known as permutation, serves as the secret of the cipher. And the last one is anagramming. This is a type of wordplay in which the letters of the word or phrase are rearranged to produce a new word or phrase using all the original letters exactly once. For example, the word listen can become silent. Now let's talk about the main topic of this video. As mentioned earlier, the Myszkowski transposition cipher is a type of columnar transposition cipher invented by Emil Victor Theodor Myszkowski in 1902. It is a type of transposition cipher used to encrypt plaintext by rearranging the order of its characters. The difference of Myszkowski transposition cipher from the other columnar transposition cipher is that the Myszkowski transposition cipher has how they handle the repeated letters in the keyword. The Myszkowski transposition cipher and the other columnar transposition cipher are both types of transposition ciphers, which means they are encrypt plain text by rearranging the characters in a certain order. However, as mentioned, there is a key difference on how they handled repeated letters in the keyword. In a columnar transposition cipher, the plain text is written out in rows under a keyword, and each letter in the keyword is assigned a unique number based on its position. If there are repeated letters in the keyword, they number it from left to right. However, in Myszkowski transposition cipher, if there are repeated letters in the keyword, rather than numbering them uniquely from left to right, you give the same letters the same numbers. This means that when you read of the ciphertext, you read across the columns which have the same number in the keyword. So the main difference lies in the treatment of repeated letters in the keyword. The Myszkowski transposition cipher gives the same number to repeated letters, leading a different pattern of rearrangement compared to the other columnar transposition cipher. Now, let's go to the encryption process. First, you have to look for the given information. Say, for example, the plain text is the tomato is a plant in the nightshade family. And here the keyword is tomato. Now you have to write the plain text in a grid, putting the keyword on top of the grid, just like in the presentation. And then Number each letter in the keyword. Note that number it using its alphabetical position, just like what is in the presentation, being A being 1, and then M being 2, then O, then T, because M comes earlier before O and T. And then read down the column. You will first read the column number 1, which in this case is column A1. So if you read it, it goes TINESAX. And then move on to the next column. But if there are number that appears more than once, just like this, column O2, O3, you have to read it from left to right, just like this. HMDALIDI, and so on and so forth. And then after doing that, you have to finish every column and then combine them, producing the ciphertext as seen in the presentation. Now, let's move on to the decryption process. So say for example, here is the ciphertext and the keyword. The keyword is potato, so first you have to write down the keyword on top of the grid and then number the columns of the grid just like what we did in the encryption process. Now we have to write the ciphered message in rows. In this example, we have 42 letters in the ciphertext and 6-letter keyword. So we're gonna need 7 rows. We will then write out the message in columns. So we need the first 7 letters and put it in the column A1, and then so on and so forth. So say for example that in this example we have these two numbers appearing more than once, the O2 and the T4. So if that happens, we have to write it from left to right. OOSITIHA, and so on and so forth. And then you have to finish off the writing, move on to the next column. After writing all the ciphertext, writing all the ciphertext, you read off the decrypted message row by row, starting from top row, and from left to right. In this example, the plain text goes, potatoes are in the nightshade family as well. Now let's talk about the strengths and weakness of Myszkowski transposition cipher. Myszkowski transposition cipher provides a high level of security, especially when used in combination with other ciphers. Another strength of Myszkowski transposition cipher is of implementation. It is relatively easy to implement and does not require complex mathematical operations or algorithms. Miskowski transposition cipher can be used to encrypt messages for varying lengths and can be adapted to suit specific requirements, which means one of the strengths of Miskowski transposition cipher is versatility. Now let's move on to its weaknesses. First, we have the vulnerability to brute force attacks. It is vulnerable to brute force attacks, especially when the length of keyword is small. Another weakness is the susceptibility to frequency analysis. It is susceptible to frequency analysis attacks, especially when used as a standalone cipher. And the third is the keyword cipher. The cipher can be compromised if the keyword is easily guessable or if it is reused. And now, to summarize the presentation, Miskowski transposition cipher is proposed by Emil Victor Theodore Myszkowski in 1902, and it is a type of transposition cipher, which means it rearranges the plaintext without changing the letters themselves. And Myszkowski transposition cipher is a keyword based. The keyword is converted into a sequence of number based on the alphabetical order of the letters. And now, this is the reference for my presentation.
Hello everyone, I am Bautista and I am here to teach you about the Playfair cipher, which is a digraph substitution cipher. So first of all, let's have a brief history on the Playfair cipher. It was the first cipher to encrypt pairs of letters in cryptologic history. The Playfair cipher was invented by Charles Wheatstone, but it carries the name of his friend Lord Playfair, who promoted its use. The Playfair cipher was also used for tactical purposes by British forces in Second Boer War, World War I, and World War II. So here's what you'll need to perform the Playfair cipher. First, you would need a modified 5 by 5 polybusis square, including the keyword or the key phrase, instructions on how you fill the square, and the keyword or key phrase, and then of course the message broken into diagrams or groups of two letters. So how to fill in your polybusis square? Fill your squares with your keyword or key phrase, omitting any repeated letter. So here's a polybusis square 5 by 5 grid. So here, for this example, we'll use the key phrase Playfair cipher, and the instruction would be we'll be filling in from left to right, top to bottom. So here it is. We filled it up with the letters from the key phrase Playfair cipher, and we omitted the letters that are repeated, just like A, I, P, and R. So next up, we will fill in the remaining squares with the remaining letters of the alphabet, arranged alphabetically, of course. So there's a note that sometimes the letters I and J are usually interchangeable or located within the same square. To fit all the letters of the alphabet, as we all know, there are 26 letters in the English alphabet, and there are only 25 spaces or squares in the 5 by 5 polybus square. And there's another note here that says that some versions omit the letters J or Q because it's not used frequently. So for this example, we'll be interchanging I and J, or we will put it as I is equal to J. So here we filled up the remaining squares with the remaining letters of the alphabet. As you can see right there, we omitted all the letters that would be repeated. So this is how you would modify or fill in your polybusis square. So now we have our modified polybusis square with the key phrase Playfair cipher and the other note that I is equal to J. So how to encrypt using your modified polybusis square? So first of all, divide the plain text into diagrams. So for example, our plain text would be I like apples. That's the message. That's the plain text message. The diagrams would divide them by 2, so it will look like this. IL, IKEA, and S. Notice that there's a blank right there. Note that if there is an unpaired letter in your diagrams, you would likely pair it with an uncommon letter like X or Q, just like that. So we notice that the S at the end is unpaired since there are an odd number of letters in this plain text. So we would fill that up with a Q or X. And also another note, if there are pairs with repeated letters, you replace the last one with an uncommonly repeated letter like X or Q as well. Right there, an example, the PP right there is paired, but it's a repeated letter. So the converted diagrams would look like this. ILIKEAPX because PP is repeated letters. We change the last one to X or Q, then LE, and then SX because S doesn't have a pair, so we pair it up with X or Q. So now we have the plain text turned into diagrams. So next up is how we would actually encrypt the message. So here's the plain diagram IL. If the letters form a rectangle, like if they're in a different column and row, use the letter on the same row but at the other pair of the corners of the rectangle made. So we have here the I and L in green. They are in a different column and row, so they form a sort of rectangle or square right there. And we use the letter on the same row of that letter that we will encrypt, but at the other pair of corners of the rectangle made. So we have here the I becomes R and the L becomes P because it's at the other side or other corner made at the other corner of the rectangle. So the encrypted diagram would be RP. So let's have a larger square or rectangle here. So if if the plain diagram is IK, you will see the I right there at the and the K is at another corner, and you would encrypt it into the other letter that is at the corner of the rectangle made. So I becomes H and K becomes B. So the encrypted diagram would be HB. Same goes for EA right there. E becomes C and A becomes F. So our encrypted diagram is CF. And also remember that the order of the letters are important. So if the first plain diagram is P, you would have to put the corresponding letter. If the first letter is P of the the plain diagram is P, you would use the letter corresponding, like the letter opposite of it on the rectangle. So order is important. Order of the letters is important. So you can't have the plain diagram be PX and the encrypted diagram would be UY. So it would be YU since you have to follow the order. So we have the diagram LE becomes encrypted into FR. And here, if the letters are located on the same row, replace them with the letter to the right. If on the same column, replace with the one below. So here we have a plain diagram of SX, and notice that S and X are on the same column, right there. So you would replace it with the one below. S becomes X, as so. And notice that the letter X is on the edge of the square, so nothing is below it. There's no letter below it. So if the letters are located on the right or bottom side of the square, wrap around and go back to the beginning of the row or column. So here X is at the very bottom, and since we have to change it, encrypt it into the bottom letter, the thing that you would do if there's no letter at the bottom, you have to go back up to that same column, so it becomes Y. X becomes Y. It would be encrypted into Y. So the plain diagram SX would be encrypted into XY. So now we just finished encrypting the message with Playfair Cipher. So here's the plain diagrams from earlier, and here's the encrypted text. Or some people sometimes you can group it up into groups of 5 letters so that it would be easier to read. So here are some examples of if the letters are located on the same row, since our example didn't have any of that. So if the plain diagram would be IH, I and H are located on the same row, as you can see. So you interchange it into the letter to its right there. So I becomes R and H becomes E. So the encrypted diagram would be RE. And here's an example if the letters are located on the same row with one letter at the end. So if the plain diagram is MD, you can see that M is at the very end of the row right there. So we would do a wraparound. M becomes B and D becomes G, the letter to its right. So MD becomes BG. So now, how to decrypt using your modified Polybusis square. Now we will learn how to decrypt your message. So what you'll need is the instructions on how you filled the square. If you remember earlier, we filled the square from left to right, top to bottom. So of course you would need that if you will decrypt a message. You will need the same instruction used to encrypt the message, to form the Polybusis square that was used to encrypt the message. So you'll need the instructions on how you fill the square, the keyword or the key phrase, a modified 5 by 5 Polybusis square including the keyword or key phrase, and of course the encrypted message broken into diagrams. So basically, to decrypt the message, you just have to inverse the steps. After modifying the Polybusis square you'll use for decrypting, just inverse the steps needed to encrypt the message. So first, we divide the encrypted text into diagrams. Let's take the encrypted text that we had previously, so right here. And the diagrams would be as so. So same tactic that if the letters form a rectangle, different column and row, use the letters on the same row but the other pair of corners of the rectangle made. So like RP becomes IL, so that's the plain diagram. Just reverse the things that you did before. So HB becomes IK, CF becomes EA, and also remember that the order of the letters are important. So YU becomes PX, and FR becomes LE. And here we are again. If the letters are located on the same row, replace them with the letter to their left. But if on the same column, replace with the one above. So the encrypted diagram is XY, X becomes S, since S is the letter above X, right? So the plain diagram, the plain text for X would be S. And if the letters are located on the left or top side of the square, wrap around and go to the end of the row or the column, like we did earlier. And since the encrypted diagram, the letter Y doesn't have any letter above it, we wrap around and go to the end of that column. So we go to the one below, the X. So Y becomes the plain letter X. And now we just decrypted the message using Playfair Cipher. So the encrypted text is RPHBCFYUFRXY. The plain diagram is ILIKEAPXLESX. So notice that it doesn't make much sense. The I it doesn't make much sense that APXLESX. So common sense would make it as P is the X next to the P, like APX, the X would mean it is actually a P, a repeated letter, and the X at the end of the message is actually omitted because it wouldn't make much sense. So here's an example if the letters are located on the same row. The encrypted diagram, example RE, the plain diagram would be IH, and here are example if it's same row with one letter at the beginning. CMD becomes DG becomes MD. So you wrap around and go back to the end of the row because there's no letter to the left of D right there. So that's the end of the tutorial, and I hope you learned something. Happy crypting!